And it's kind of the first part of electrochemistry. So electrochemistry is taking chemicals and making electricity from them. So electricity is moving electrons. So taking chemicals. So anytime we can get a transfer of electrons, if you get electrons to move, you get electricity. So these would involve redox reactions. Any change in charge means there's a transfer of electrons. This is a table here of something called standard reduction potentials. Okay, so it's the ability to be reduced. Who has the best ability to be reduced? Who's not being reduced? So think about being reduced. Reduced means you want to gain electrons, okay? Want to gain electrons. So this looks a little different than the table I have for you guys, but again, this is showing you can find oxidation, you can find standard oxidation tables. This just happens to be a reduction table. And it's going to tell you some voltages of some things as they're reduced. So for example, F2 as a gas has a great ability to gain electrons, better ability than anything else on here to gain electrons and become F negative. It really wants to gain electrons, has a high electronegativity, wants to gain electrons. Its reduction potential is 2.86 volts. Okay, now you probably don't know what a volt is, okay? A volt is a potential difference between two things that makes electrons move from one spot to another. So technically a volt is 1 amp, 1 ampere per 1 ohm. So it's really the amount of current that flows through something. An ampere is an amount of current, okay? And an amp is considered to be 1 coulomb of charge per second. All right, it still doesn't get into chemistry necessarily. A coulomb is, I looked this up, remember this number, 6.241 times 10 to the 18th electrons. So when you start seeing voltage, more voltage means more electrons. Okay, a volt is 1 amp per 1 ohm of resistance. An amp is a coulomb of charge per second. A coulomb is this many electrons per second. So we can kind of consider that a volt is producing this many electrons. So more electrons, more voltage, okay, or a better ability to transfer electrons, more voltage, okay, and a better battery is what we're going to be talking about here eventually, is making batteries. So batteries are made from chemicals that can transfer electrons. Batteries are made from chemicals that can transfer electrons. So again, these are redox reactions that are happening inside these things. So this is a table of reduction potentials. And as we go down it, things get worse and worse at being reduced. So F2, like I said, is the best thing to be reduced. Silver ions, they have a +2 charge. They have a decent ability to gain electrons and become more silver ions, or even silver, solid silver. Here's gold as a +3 charge. Gold is a +3 charge, can gain 3 electrons and become gold. Has a reduction potential of 1.52 volts. Okay, you're probably not going to use gold in a battery to make electricity because it'd be too expensive, but those are things you can use. As we go down the table, we get to a certain spot that is a 0. So this is everything's based on hydrogen. A hydrogen ion gaining 2 electrons, becoming H2, they assigned a value of 0, a reduction potential of 0. That means the opposite is also 0. H2 gas losing 2 electrons and turning into aqueous hydrogen ions, they assign that a reduction or oxidation potential of 0, depending on which way you're going. Remember, the opposite way would be oxidation. This way is reduction. So as we go down here and look at lithium, has the worst ability to be reduced. A lithium ion does not want to gain an electron and become back to solid lithium. It'd much rather be a lithium ion. It wants to get rid of its electron. So in other words, it has the best ability to be oxidized. It has an oxidation potential of positive 3.04 volts. Its reduction potential is negative 3.04 volts. So it does not want to be reduced. So things that have negative reduction potentials do not want to be reduced. They would rather be oxidized. So again, if we flip these around, it is an oxidation potential. So if you made something with fluorine, that has a really high reduction potential, and lithium that has a really high oxidation potential. Very high voltage there. All right. I'm going to pause for just 1 second. All right, here's going to be your notes on this stuff. So we're going to be talking about galvanic or voltaic cells. They're just batteries. They're just batteries, making batteries from chemicals that can transfer electrons and make electricity. So converting chemical energy into electrical energy. Again, redox reactions. These are spontaneous redox reactions, okay, ones that will happen, and they involve an external transfer of electrons. So galvanic, voltaic cells, same thing. It's just a battery being made, okay, just a battery. So let's say here that we have a reaction of copper in a solution of silver nitrate. Okay, let's write the full equation out here, so we can kind of see that again. So copper as a solid plus some silver nitrate solution that's aqueous. Going to make some copper nitrate solution that's aqueous plus some solid silver. So let's write the net equation for that. Our net would be, whoops, I just erased that. Our net would be, solid copper with no charge plus your silver ions making some copper ions, making them copper plus 2, plus some solid silver. Remember, this would be blue as it dissolves. We need a 2 here and a 2 here. All those coefficients will not affect us very much in these things. So if we write the oxidation half reaction, remember oxidation is losing oil. Oxidation, oil. Oxidation is losing rig. Reduction is gaining electrons. So losing electrons, gaining electrons. Copper is losing electrons. Silver is gaining electrons. It's being reduced. It's being oxidized. So our oxidation half reaction is copper going to copper plus 2 electrons. And our reduction would be silver ions gaining an electron, turn into Ag. And we can put a 2 in front of all those things so that everything is equaled out. So there's our oxidation and our reduction. So there is a transfer of electrons between those. Anytime we get a transfer of electrons, we can make a battery. We can make electricity from that if we can get the electricity to flow through a wire. Okay. Some things you need to remember. Some terms here. Well, let's move this up. Some terms when we're making a battery or a cell. Anox. Oxidation occurs at the anode of the battery. Oxidation occurs at the anode. Red cat. Reduction occurs at the cathode. Batteries have a positive and a negative end. Positive and negative end. So reduction occurs at the cathode. Oxidation occurs at the anode. Fat cat. Fat cat. Electrons flow from the anode to the cathode. Fat cat. Electrons flow from the anode to the cathode. Then oil rig, you know, oxidation is losing, reduction is gaining. So oxidation occurs at the anode, reduction occurs at the cathode. Electrons flow from the anode to the cathode. All right, let's draw a little cell here. Okay, draw a little cell, and I'll show you one so you see a little bit better example than my little drawing of it. But here's what we have happening. Actually, I might show you this first. I don't know if it's the same one. Here is a battery actually happening. All right. Here's what we got going here. Let me pause that for a second. So this is going to be a battery. So this is a wire where electrons can be transferred. So if we get electrons moving through a wire, we have electricity. Electrons moving through a wire, we have some electricity. So this is making some electrons move. This is not the same as what I had before. This one has copper and zinc. So this is zinc. This is copper, zinc, copper, zinc, copper, solid copper. So I know it has a +2 charge there, but this is 0 charge and 0 charge. So some solid pieces. This is suspended in some zinc sulfate solution. So that means there are some zinc ions in here and some sulfate ions. This is suspended in some copper sulfate solution. So there are some copper ions and some sulfate ions. Okay. Well, if we look at our reduction potential sheet, reduction potential, you look and see who has a better ability to be reduced, copper or zinc. And I don't know if I have a list of this. Copper's reduction potential is 0.16 volts. And I don't see. And zinc's is negative 0.76. Okay, so copper has a better ability to be reduced. Copper's got a higher voltage on that sheet. I'll come back to that. It's got a better ability to reduce. So what's going to happen here is electrons are going to flow towards the thing that gets reduced. Okay, so electrons are flowing out of here, going that direction. So electrons are flowing into there. They will jump into the solution. Okay, and when electrons hit this copper +2, the copper +2 gains 2 electrons and turns into solid copper, and adheres back to there. So this piece of copper is going to be getting bigger. These copper ions are coming out of solutions. You'd see this blue solution starting to lose its color over time. Copper ions are starting to form into solid copper. Well, our zinc here, every time a zinc loses 2 electrons, it turns into aqueous zinc. So this would be getting smaller. Okay, so electrons are flowing this direction. Remember, fat cat. Electrons are flowing from the anode to the cathode. If you think of it this way. Electrons are leaving here, oil rig. Okay. Oxidation is losing. So zinc is being oxidized. Okay, that means this is our anode. And oxidation occurs at the anode. Red cat. Reduction is occurring at the cathode. So these electrons are flowing here. Again, every time electrons leave here, the zinc solid is turning into aqueous zinc. So we're getting lots and lots of zinc ions here. So we're building up lots of positive 2 charge. Well, the coppers are gaining electrons and turning into solid copper, so we're losing the positive charge there, which means we're going to have lots of SO4 -2s over here, plus we're getting electrons in here. Well, the battery wouldn't last very long if we kept doing that, because electrons won't flow to a negative area. And if this starts getting negative in here, they won't flow into it anymore. If we're getting lots and lots of positives, electrons will stay over here. So we also have this salt bridge that would be dissolved potassium nitrate. So you have potassium ions and nitrate ions in this. They can flow either direction. Well, we're building up lots of positive here. So NO3 negatives start to flow down into that to balance the charge. And potassium ions start to flow into this to balance out that charge. So our battery will keep working and producing moving electrons. So let me get this going again. So again, electrons are leaving here. Oxidation is losing. The zinc here is being oxidized, turning into zinc +2s. NO3 negatives are coming out of our salt bridge. Electrons are going over here. They jump into solution every time these electrons touch a dissolved copper ion. That copper turns into solid copper. Dissolved copper turns into solid copper. Our battery keeps going until we run out of materials to keep reacting. So there's a little battery. Again, this is called the salt bridge. All right, let's go back to our notes. All right, back to our notes. Here's our oxidation and our reduction that's happening in this. So we need to figure out the reduction potential of this and the oxidation potential of this. So I look in that chart that I had up earlier and find the reduction potential of silver. And the reduction potential of silver +1 ions, silver being reduced from +1 down to 0. Reduction potential is 0.8 volts positive. So silver wants to be reduced pretty well. Copper, so that sheet is oxidation potentials. I'm going to flip that, and it's being reduced, so I have to change that. It's oxidation potential. Copper's oxidation potential is negative 0.34 volts. So really, it wants to be reduced. Its reduction potential would be positive 0.34 volts. So it's got a better ability to be reduced than it does to be oxidized. But As long as there's a difference in these two, we can make a cell or a battery. As long as there's a positive difference. We need it to be positive. Okay, we need a positive value. It has to be spontaneous, which means this has to be a positive value between these two. So if we draw our little cell here, our battery, so over here, we're going to have our piece of copper, solid piece of copper, in some aqueous copper solution. Okay, it could be copper nitrate, something that has dissolved copper in it. Okay. We would have a wire connecting with probably a voltmeter in the middle. Okay, over here to our piece of silver suspended in some silver nitrate or some kind of silver solution. All right. We would need a salt bridge between those two. So I'm going to draw a little salt bridge here. I didn't do a very good job of drawing this. It's a long ways apart. Usually I would draw these much closer together. Sorry about that. Salt bridge there. And most common thing in our salt bridge is we put in some KNO3 solution. So potassium ions and nitrate ions can move to balance out the charge. Okay, so who's being oxidized, who's being reduced? Well, copper's being oxidized. So this is our anode, and you could draw the anode on either side. Okay, it could be either side. This is our cathode. A reduction is occurring. All right. Remember, electrons flow from the anode to the cathode, so electrons are going to flow. Electrons are going to flow that direction into that solution. Electrons are flowing from the anode to the cathode. So our silver ions are being reduced and turning into solid silver. Our copper is being oxidized. It's losing electrons and turning into aqueous copper. Our voltage of our cell, the cell voltage is equal to the reduction potential plus the oxidation potential. So our reduction potential would be 0.8 volts plus a negative 0.34 volts. So 0.46 volts is our cell potential. This is 0.46 volts, or voltmeter would read. That's the voltage going across this wire. The number of electrons in here does not matter. The fact if this is a 2 in there, that potential stays the same. Okay, potential stays the same, just so you know. All right, so oxidation, reduction, electrons are flowing that direction. Okay, our KNO3. So since we are getting more and more positive charge over here, the NO3 negative ions will move there to balance out that charge, and the K plus ions will move into there to balance out that charge over there. Long video, lots of stuff. You can figure this out.